evening. My name is Blake Nancarrow, and I wanted to talk this evening about double stars. Take our discussion a bit further than before. Back in February, I don't know if you saw my presentation then, if you've seen it online or you were here, but back then I was talking about how you could observe double stars just for fun, for their colors, for maybe some challenges when observing. As Andy indicated, sometimes you may not see the faint companion to a star, but that's something that I like about them, is going back to them or returning to them. But I wanted to kind of kick it up a notch this time. I wanted to talk about how you might measure double stars. The same way that amateur astronomers can contribute to science, can do citizen science, perhaps from their backyard, double star observers can similarly collect data and submit that, and it can contribute to the body of knowledge that we have about double stars, but that in turn can be used to give us information about star systems, the masses of stars, orbital details of those star systems, and that in turn helps us with stellar classifications of stars, helps us refine the distances to stars, which is used in the cosmic ladder. So there's actually quite a lot that you can do, that you can contribute to this sort of hobby. So again, back in February, I talked about sort of looking at double stars just for fun, for their beauty, for their colors, and I reminded people, or wanted to remind people, that double star observing can be done anywhere, anytime, partly because we're looking at starlight. Thin beams of light can punch through light pollution, so you can do it in your backyard very easily. You don't have to drive out of town. But again, I wanted to talk about how you might measure double stars. Now, you can do things very casually. I don't want to suggest you have to spend a lot of money and buy a lot of accessories, although you probably are going to do that anyway. But you can casually measure double stars just by keeping good notes. You're supposed to do that, right? You're supposed to keep good log notes and things like that. Paul Markov, who's not here this evening, he's an advocate of that. I just do that. I'm always keeping detailed notes of my observing sessions. This shows you a sketch that I did of Myram, Eta Persei, and I noted the stars, or I've annotated this diagram to show the A, B, C, and D stars. And if you look near the top right of that sketch, you'll see that I've also noted the direction, the east direction. And by inference, I know, because I made a note about the telescope and that I was using a mirror diagonal, I can figure out, or I know where north is. It happens to be, I don't show it in this diagram, but it happens to be up near the top left, sort of the 11 or 10 o'clock position in that sketch. But looking back at this sketch, I can assess how far apart those stars are, roughly. And I can get the angles of the B star and the D star and so on in comparison to the A. So if you do a good sketch and then you refer to that later, you might be able to get some good information about those stars. So you can do a very casual form of measurement. And if you look at something like a binary system, that can be very interesting because they may change over time. I don't know if you know this or have thought about this, but some double star systems that are interacting, that are binary systems, that is to say one star orbits around another star, that they may have periods that are 50 years, 100 years. So that means if you go back every year, every season, and you look at that star again and you compare it, its new or current position, to your previous notes, or you do sketches each year and you compare those sketches and you do a flip book, you might see the stars, or you can detect from your notes that the stars are changing. Did you know that Sheraton, or Beta Aritis, the second brightest star in Aries, has a period of 107 days? So that means you can look at it a few times in the same season. And in theory, you can see the B star moving around the A star. Now, a lot of binaries are very close, so you may have to use very high magnification, but that's a cool thing. That was one of the things I mentioned in my first presentation, that binaries are dynamic, that they're changing. Some of them change. So we're interested in binaries. These are the ones that we want to measure. This might, for some people, make a shift or be perceived as a change in observing, that it's becoming work. Dave Cotterell, who's an active double star observer in the North York Astronomy Association, he says, I'm going to work tonight. And that means he's using his telescope and doing some measurement of double stars. So you may not like that sort of aspect of it. But if we take two measurements, it's easy to do. We measure the angle that the stars are in relation to one another, and how far apart the stars are from one another, the separation. And you do that repetitively and keep good notes, then you can collect some good data. And almost immediately you could, if you wanted, calculate the mass of the total system. With those two numbers, we can start to do that. Preliminary orbital data can allow us to calculate the mass of the system. More complex math is needed. You don't have to do that. I'm not strictly interested in that, but more complex formulas can determine the full orbit, and we can start to get the masses of the individual systems when we do spectroscopy and so on. But just getting those two numbers starts to fill in some important information about binary star systems. So it's important data. Ron Tanguay, who's a notable double star observer and contributes to Sky and Telescope magazine, he said, because so few professionals remain in the field, qualified amateurs are badly needed. So you can help. You can contribute here. This is something that's easy to do. If you were to look at some stars over a long period of time, I'm not suggesting that you do this strictly, but if you were to observe a bright pair of stars over a long period of time, you might notice that they're moving, but maybe not around each other. They might be moving in relation to the background stars. So this image here is showing you the image of these bright stars over about a 50-year period. First shots in 1954, second one's just a few years ago. Let me do a doodle here if I can. That the small star kind of ends up over here and the bright star kind of ends up over here. Do you see that compared to the two sketches? So this star is moving, that direction, trying to do some little arrows here, and that star is moving that direction. So these two stars are moving through space together. They're like two dolphins swimming off the bow of a ship going the same direction. They're going the same speed. We're not interested in these, per se. These are stars that show high proper motion, and these we sort of discount. You can see that these two stars in relation to each other, if I can get the centers here, and the distance that they are from each other, that angle and that separation doesn't appear to be changing. It may be. But these two stars just seem to be moving through space together. They're not going around each other. So there's no apparent change in their angle or their separation, okay? So those ones we're not interested in. We want to focus in on stars that are binary systems that appear to be going around one another. So once again, if you looked at two stars over a long period of time and you saw that one was moving closer to the other star and then far away, the angle of it was changing over time, then you know you're on to something. Now, I forget where I got this image. Doesn't matter. You can see there's multiple observations, though, the little green pluses. And then there's other observations that are photographic with the blue dots and the purple dots and so on. But let's say the first observation was out here of the B star. So it's quite far away from the A, and it has a certain angle, whatever that is. And let's say we look at it 10 years later, and multiple observations are coming in, so it's over here. It may be very difficult to determine if the angle changed early on, but we can see it's much closer. It's a third of the way closer to the other star. Another 10 years pass, and we look at it again, and the angle is markedly different now. And it's much, much closer. And then another 10 years later, it may be so close, in fact, to the A star, we can't see it anymore. We may lose sight of the secondary star, but a few years later it shows up again, and it's clearly on the other side. Now the angle is this way as opposed to this way. So when we see that, when we see a star changing its position, its angle, and the distance from another star, with actually remarkably few measurements, we can get a preliminary orbit, and then we can start to calculate mass and things like that. So this is a lot like moons around planets. It's like objects in our solar system, and the physics is the same. It's Kepler physics all happening here. So these are the ones that we want to measure or maybe photograph. When we start to see these arcs, then we know that there's orbits going on. There's some famous ones. Sirius has a faint companion, Sirius B or Pup. Anybody seen it? Anybody seen the Pup star? It's very, very challenging because the A star is so bright and the B star is very dim, but you can see it helps if it's far away in its orbit. But in 1992, 93, people were probably very challenged at spotting the star there. But in the late 60s and 70s, I don't know where it is right now currently in that path, but we could figure that out. Repetitive observations allow us to get more and more data. This image reminds me to remind you that visual observing of double stars is still quite relevant from the point of view that the human eye has extraordinary dynamic range. Ralph Chu will assure us of that, compared to chips or detectors in camera equipment, which don't have as extensive or as broad a dynamic range. That's getting better and better all the time, but it's still worthy, some of these types of targets, for visual observation because of what the eye can detect. So that's kind of cool. Bit of early history, really, really quickly. It was actually John Michel back in the 1700s that first suggested that stars might be related, that they might be gravitationally interactive. And that was kind of a radical thought at the time, but we don't think twice about that now. That's sort of common knowledge. William Herschel started observing double stars, and in the early 1800s, he had taken measurements of many and recorded the changes in relative position. So he saw stars moving around each other. Felix Savary in 1827, he computed the first orbit of a binary system. So you can see that double star observation has been going on for a long time. The golden age was in the late 1800s and early 1900s. Now we have the Washington Double Star Database. This is the warehouse where all the double star data is collected, and you can easily look up information there. There are hundreds of thousands of entries in the WDS, but remarkably, we have very few stars in that catalog where we have good, known, obvious orbital data. So there's a lot of gaps. There's a lot of missing data. We need more data there. They actually, the stewards of that database, they actually note stars as neglected double stars. So you can look up the neglected list, and these are ones where there hasn't been data collected for the last 100 or 200 years, or the data is confusing, that current observations don't show a double star where it was noted. So they appeal to amateur astronomers to look for this, to go after those neglected double stars, to get current data, to fill the gaps, to get more current information. So again, you can add to this legacy pretty easily. I don't suggest you get one of these. This is what people used in the old days. This is a filar instrument. It's got 2 wires in it, maybe 4, but one is fixed, and those dials and knobs can move one of the wires, or they're opposed, so you can move one up and down, move the other one up and down, and the whole thing can be rotated so you can get angles. If you could find one of these, they're probably very expensive. These old antiques, I can't speak to the quality of them. I've never looked through one of these, but that's what the early astronomers used to measure double stars. The modern solution, it's not too expensive, is to get an astrometric eyepiece, and it has graduations in a reticule that you can use to assess distances and angles, and I'll show you some of those. I've been looking around for do-it-yourself solutions. You know, I like doing that, but I haven't found any that are really compelling. So you want to measure 2 things. I mentioned this before. You need the position angle, and you need the separation. Separation, sometimes called sep, is formally measured with the Greek character symbol rho, and we measure that in arc seconds. Even very wide doubles are typically shown in arc seconds, 300 or 320 arc seconds or something like that, as opposed to switching immediately to arc minutes. The angle, of course, we use degrees for that. It's officially noted with the Greek character theta, and it's sometimes called just PA, position angle. But we need a reference point. We have to use north for that. So you can see we start at north and we travel through east to get the reference. That's 90 degrees and so on. Now from my little diagram here, we can't assess the separation. We don't know how big that scale is. We have no idea what that is. But the position angle, we could figure that out by eyeballing that. What do you think it is? What do you think the separation angle is there? What do you think? 225? Final answer? Don't want to phone a friend? Okay, 225. I agree that if you go through, again, east, 90 degrees, south is 180, and it's about halfway, I think, between south and west, so add 45 to the 180, 225. So that shows you, again, from a good sketch or just eyeballing it in your eyepiece, if you know where north is, you can maybe get the angle pretty easily. If you know your field size for your eyepiece, you know what the edge-to-edge field size is, that's the true field of view, the TFOV for your eyepiece, then you might be able to estimate the separation pretty easily as well. But here we could only guess. Of course, knowing where north and west and all that is in your eyepiece can be a bit confusing, especially to the beginner astronomer, because fields are presented in a funny way in a telescope. When you look at the sky, things are backwards, right? East is on the left, as opposed to on the right, like a terrestrial chart. So that throws people. But if you look at the sky, north is presumably up. If you look with binoculars at some object, east is going to be counterclockwise from north, and that's how you would measure the position angle or the theta from there. Lots of books and websites on this subject really convolute matters. I've seen very complicated tables to explain how your field of view should look, but it's super simple. You just need to count the reflections in your telescope. If you have an even number of reflections, then you have a rotated field. It's just north is down. Everything is going in the same direction. You're still going counterclockwise to get your position angle. If you have an odd number of reflections, which is very common in an SCT telescope, and you got a mirror diagonal that you put your eyepiece in, or a star diagonal, or a refractor, and you've got a star diagonal for comfortable viewing for a telescope. When you have a SCT with a diagonal, you have an odd number of reflections. So just count the number of times the light is bouncing inside your telescope, and then you know which field of view you have. If it's a mirrored view, now you calculate your position angle clockwise. So that requires some familiarity with your equipment. You got to think about that a little bit. West is easy to figure out though, right? super easy to figure out where west is in your telescope, assuming you have an equatorial mount telescope with a motor drive. Just turn the motor off for a moment. And all the stars, everything will start shifting through the eyepiece, and where they fall off the edge, that's west. Just like the sun is setting in the west, the stars will set on the west edge of the field. So it's easy to figure out west, and if you know about your telescope equipment, then you'll know where north is, and you can update your sketches or drawings accordingly, or your log notes accordingly. And if you're very familiar with your telescope equipment, you'll know what the field of size is, how far it is across from one edge of the field to the other edge of the field. Is it 1 degree? Is it half a degree? Is it 26 arc minutes? If you know that, then you can start to estimate separations. If you know that this is a 1 degree field, you can see the A and the B stars are quite far apart, almost half a degree here. So you can start to calculate those things pretty quickly. Here's what I think you need, though. Of course, we need lots of telescopes. There's Bobby with Bobby Abraham with his Dragonfly instrument. So I don't think you need that many telescopes for doing this. But ideally, you want a motorized telescope. You don't need a go-to, but a telescope that can do tracking on an equatorial mount is ideal. Usually we need magnification. You want to increase the magnification when you're looking at double stars. Obviously, tight double stars become further apart when you magnify them, so that helps. And then that lends to greater accuracy when you measure them. Part of what we need to do is not necessarily trust the quoted values for our telescope equipment. So the true field of view, it may not be accurate. It depends a lot on the telescope system and so on. So it's best to measure your field size by doing drift timings. You let the star move across the field and you time that. So you need a stopwatch or a timer app. If you've got a good stopwatch on your wristwatch, or you've got an app on your phone, if you've got lap timing, then you can do repetitive runs. So keeping notes for all this, I have little spreadsheets on my little computer, usually with me in the field or at the telescope. So I'm punching data into my spreadsheet, and I'm doing on-the-fly reduction of some of that data. And the one thing that you might want to consider, this can be a bit expensive, so I'm starting to spend a bit of your money here, is getting an astrometric eyepiece, which has a reticule in it and a graduated scale. I've got one here, and I'm going to hand this around. So I'm going to take the cap off of it here, and I'm going to turn on the reticule so you can see in it. So look inside here and see if you can see the reticule, and then hand that off to somebody else. I've got the other cap on, so keep that on so it's dark. So it's like looking in outer space. So check out that. That's the Celestron astrometric eyepiece, and I'll show you some information about that here on the screen. So you may have this piece of equipment already. To increase magnification, you may need a Barlow or a PowerMate. And your objective is to get the focal length of the telescope, if you're going to do accurate measurements, to over 3 meters. If you have an 8-inch SCT telescope, you're 2/3 of the way there. That's a 2-meter scope. So you just need to 2x times doubler to get into that 4-meter range. If you have a small refractor, you might need a 4x to measure double stars with some accuracy. I have a 2x Barlow, I have a 2x PowerMate. We have a 4x PowerMate up at the Carr Astronomical Observatory. You can borrow those. You can borrow mine if we're near each other. Here is one of the astrometric eyepieces that's available. This one's a bit less expensive. I've seen it for around $110, $120 Canadian. This one's from Meade. Once again, you can see that it's a 1 1/4 inch eyepiece. It's got this stalk sticking out of it with the battery and the illuminator and an on-off switch. Don't forget to turn the switch off at the end of your observing session. It's got those little button batteries, expensive button batteries in it. You can see the inside illuminated reticule scale. It's got a linear scale that has 50 divisions. It's got a large circular scale with 360-degree markings on that. So you can use that for position angle, or the half protractor. So there's a couple of things specifically for doing double star work here. The crosshair thing here, very rarely used now, but people use this when they did manual guiding for astrophotography. I don't know of anybody that does that anymore, but you could use that for this. There are other uses for an astrometric eyepiece. You can measure the distances between moons and a planet. You can measure the size of a planet. So there's other things that you can do, and even just telescope setup. If you want super precise go-to performance out of your telescope, you know, when you're setting it up after you've done a good polar alignment, you're supposed to put your target stars, your target alignment stars, right in the center of the eyepiece. How do you do that? Super easy if you have one of these. So you might be able to use an eyepiece like this for other purposes than strictly double star work. I have the Celestron one. I actually went looking for the Celestron micro guide, and I was having a hard time finding it. A lot of places were showing it out of stock, and it wasn't being replenished. So I was getting worried that you couldn't get them anymore. But then I started stumbling across the Bader Planetarium micro guide, and they look exactly the same. And I realized what was going on. That I don't think Celestron ever made their own. They contracted Bader to make it, and then they badged it as Celestron. So you can buy the Bader Planetarium micro guide, and it works and acts exactly the same as the Celestron one that's going around the room. So once again, it has the illuminator. Here's the reticule. Notice it has 60 divisions. The linear scale has a split or a channel down the middle. I like that. You can do your drift timing and make the star go down the pipe. So that's kind of nice. It's a little bit more accurate. It's got that protractor. The large circular scale has two measures. I don't know if you can see it, but there's numbers going clockwise, numbers going counterclockwise. So it works for the two types of views that your telescope may present. So I like it. It's a personal thing. Some people like one versus the other one. This one appears more expensive, though. When I did some quick checks online, I was seeing prices around $300 or $200. So it looks to be more expensive than the Meade, but to each their own. So those are your sort of options. Now I thought what we could do is a little demo of how to do measurement. There are lots of ways to do this. There's the Celestron way. I followed those instructions. I read Ron Tanguay's method. I tried that out. Tom Teague wrote an article on Sky and Telescope, and it was quite good. It took me a long time to master his technique, but it allows more accurate results pretty easily. So I've tried his method there and built spreadsheets to collect the data and so on. So I thought we could do this. So I'm going to run a Stellarium here and just try to simulate this. So bear with me for a moment as I get Stellarium going. Built into new versions of Stellarium are the astrometric eyepieces, so you can actually see what it will look like in a telescope, and you could do practicing or trial runs inside the software, so you could practice it or get used to it here. So give me a second. So here we go. This is the evening sky right now. And let me just advance a little bit in time, just to darken the sky. We'll turn on some constellations. We'll turn on the meridian. There's some of our stars. There's Cygnus. So I'm just interested in something here. I'm going to use an example star, 16 Cygni. So let's try that star. There it is. And we'll zoom into that. Does it look like a double? No. So we need high power here. So if I zoom in a lot, there it is. There's the pair. Okay. So I'm going to turn on the eyepiece view now in Stellarium. So this is simulating what it looks like through a particular eyepiece. Now I can't quite read those descriptions way over there, but we have a 40 millimeter in a 14-inch telescope. Okay, I'm going to switch the oculars. There's a different one. There's a 26 mil. There's a wide field one. There's another wide field. There's a binocular view. And now I'm going to switch one more. And, oh, it didn't show up, the micro guide. There's the Meade micro guide. Let me back up. I tried to get there's the Celestron one, okay? Now bear with me for a second. I'm just going to shut off the scaling so it's bigger for us there, okay? And I'm going to increase power. So I'm going to put a Barlow. There's a 2x. There's a 3x Barlow in the telescope, simulated telescope. And I'm going to rotate, wrong way. And this is just spinning that eyepiece in the telescope. And I'm just trying to line them up. And now you can help me. Let's count the ticks from the one star to the other. I put the A in the middle. Doesn't really matter for this purpose. But what would you say? Yeah. So we count the ticks. There's 15. It's somewhere in the middle there. Okay. So I've got a little spreadsheet here. We'll pop that in here to our little spreadsheet. So how many ticks did we say? 15 and a half maybe? Yeah. 15 and a half. Okay, so I'll pop that in here. But what we need to do now is figure out how big that scale is in real space. We need the angular measurement of this. We need the scale of that. So what we have to do is drifting. So I'm just going to click away from the stars for a second and see how they're drifting. So that's telling me where west is. Okay. And I'll just back up time a little bit. Oh, too much. So we'll just speed that up a little bit. So I'm just trying to get the angle here right. And I'm trying to get the star to run along the scale. How's that? That's pretty good, eh? It's not perfect, but it's close enough for our purposes. Now I need you guys to help me again with this. What we're going to do is we're going to time this. So somebody want to fire up a stopwatch? A couple of people could do it. We could average it and stuff like that. So I'm going to put the star off to the edge here, okay, and we'll get ready to start it. So I'm going to let the star start moving, and when it crosses the marking, I'm going to say go. We'll let it run all the way across the scale, and when it gets to the end, I'll yell stop, so we'll get our timings there. You ready? I'll back it up a little bit. Okay, get ready. Get ready, and go. I don't know if you've done asteroid occultations, but the delay between when you hit the start and stop on your stopwatch, that there's delay, there's a human factor there. It's called personal equation. You have to factor that in. Get ready to stop. Stop. I was a little bit early there.
15.45 seconds.
15.37. Pardon me, what was that? 15:57? So we're around 15 and a half?
Yeah.
Anybody higher than that? 78. Pardon? 78, okay. So maybe 15.5, 15.6, something like that. That's our number. You do this a dozen times, right? And you take the average, so you got a low standard deviation, low error here. Now I'm leaving the star at the edge there. I'll come back to that. But let's go to our spreadsheet again now, and let's put in that number. So our drift time was, say, 15.6 after we've done a dozen repetitions there. And my spreadsheet, doing some trig math, we've calculated the row or the separation in a real world measurement at just over 38 arc seconds. All right, we'll check that in a minute to see if it's any good. Now what we'll do is one more thing. The quick and easy way to get the position angle is to use the protractor. So I'm going to put the star on the 270 mark here, and I'm just going to move the stars over here, and I'm going to put the A star, which is the top right, as close as I can into the protractor. Okay, so you do this very accurately, very carefully, and now we start to use the protractor scale. here, and we figure out what's going on. And again, you would look at your outer circle and go clockwise or counterclockwise, depending on the view of your telescope. So that's 0, this is 30, and so on. What do you think we are? We're over 130, 132 maybe, 133, something like that. So it depends, again, how accurate we are in this. And I was off a little bit, so I'm off about a degree here, but close enough from an airplane. So we've got some good numbers there overall. So thank you, Stellarium, for that. And back to here. So what do we get? If I look up this information in SkyTools, you can see that we get a separation of a separation of 39.8. We were pretty close, eh? We were around 38 and something, just from that quick measurement. And we got a position angle, it was around 132 maybe. From our eyeballing it, SkyTools says it's 133. That's my SkyTools software numbers that I'm quoting here, but that's not the official source. So let's go look it up at the official source. And we know that's the Washington double star database. So let's go check it out. So here we go. Here's the Washington double star database, and the 16 Cygni has an RA that's around 19 hours. So we'll go into the 18 to 24 section. This is a huge list. Again, there's 100,000 entries. This one's got about 25,000 entries here, so I'm just waiting for it to build. You need to know the discoverer name for this star. 16 Cygni is also known as Struve from the first appendix 46. So Struve A 46. So I'm going to type in STFA 46, and there we go. Here's the listing for that double star. And there's 2 entries here. It's a triple, actually. But you can see that the first recorded measurement was 1800. That's when this star was first measured. And the position angle then was 141 degrees. But now, or at least as of 2017, the position angle is 134. We were very close, just off by 2 degrees, right? And the early separation measurement was 37, but it appears to be moving farther apart. Looks like it's a binary system, maybe, or the 2 stars are moving separately with proper motion. The proper motion, some of that data is over here. But you can see the current separation is 39.8. That was the same number that was showing up in my software. So we got pretty good numbers, eh? So congratulations, you've measured your first double star. Woohoo! Super easy. So with those eyepieces, it's really easy to do, except it's boring and repetitive work. You're supposed to do lots of iterations of the timing so that you've got good quality data. You want to measure it a couple of different ways, do cross-checks along the way and stuff like that. Again, I've used a lot of different methods with those astrometric eyepieces to sort of come up with a good technique. I've got my own workflow now. I found efficiencies based on Tom Teague's method, and I've got my pre-built spreadsheets, and I do some cross-checks along the way, so I know that the data that I'm collecting is in the right direction, that I'm measuring things according to the correct orientation. But still, there's no right or wrong method that you can use for doing this. There's lots of different techniques. So are you interested? Want to do it? So go out and buy, or if you have a birthday coming up, and how many shopping days are there till Christmas? So you could put that on your list there to get one of those eyepieces. But you don't have to do that. You can measure these just for fun with detailed sketches or good notes and eyeball separation and position angles. You could do that pretty easily, but just keep good log notes then. But if you are getting more serious about this, getting an eyepiece that you can use to measure this and measuring it accurately and coming up with a good method and getting consistent, and maybe starting out by comparing your results for a double star that's not a binary, use a non-binary system and measure it and see if you can come up with the same numbers and get good results. And we can talk about in the future how you submit that data, how you write a scientific paper and where you send it. One of the best books on the subject is the Observing and Measuring Double Stars. I've had this for a few years. This is the 2nd edition. So very nice book on the the subject, and it talks about different measurement techniques and how orbital data can be calculated. So you can have a look at that if you'd like. I mentioned the Journal of Double Star Observers. That's one of the clearinghouses for submitting papers. So go to their website, start looking at their website and reading other articles about measurement techniques and seeing papers that people are contributing, which includes high school students and their teachers. That's one of the most common sort of submission. They do work over weekends. Of course, lots of resources are available online, and to toot my own horn, you can visit my blog and use the double star tag, and you'll find all kinds of articles there. And if we're observing together, I'm happy to help, and you can borrow my eyepiece. I'm doing more and more stuff photographically now, so I can reduce the data in warm temperatures without mosquitoes at a later time. This QR code, if you want to scan that, that'll bring up the article. I have posted everything that I've talked about and some images on our website, so you can review that article. And I don't know how much time I've taken. I could take some questions if the Master of Ceremonies will allow me. So, any questions for me about double star measurement? Yes. Oh, waiting for the microphone. Yep. Is that Chris? C'est moi.
So I assume you can do a lot of these measurements for your particular setup, and as long as you don't change your setup, you've got some of that homework already done when you do a session. Is that correct?
Yeah. So if you set up over a weekend and you don't touch the scope, in terms of the optical path, you don't change the optical path, then you can use the data that repetitively. But we know that things can happen, right? You can get thermal changes in a scope. It's encouraged that you do drift timings over more than one evening. Ideally, you do the position and separation measurements over more than one evening, because of seeing conditions and other factors like the elevation of those stars, and if you're getting refraction factors from the atmosphere. So you can do things quick and dirty, and if you leave this telescope set up the same, and that includes a doubler that you had in it and things like that. Remember that a telescope like an SCT or designs like that, where when you focus the primary mirror, it's moving the whole mirror, the optical length, the focal length of the whole system changes there. So that might mean on night 2, if you focus differently than the night before, if you have both an internal and an external focuser, you have to assume it's different now. So you might have to redo your drift times to get the proper scale. And it might only be a little bit different, right? 1 percentage point, but that could affect things a bit.
And second question quickly, if you're investing in astrometric eyepiece, then you've got to choose the focal length that's appropriate for this likely star separations, is that right? And you could then go with the Barlows or the power meets to change
You
the
don't
scale.
have any say really in terms of the astrometric eyepiece. The mead is 12 millimeters and the Celestron Beta one is 12.5. So that's a given. But factor that into the telescope that you're going to use that with, and then that will drive what Barlow or what magnification that you need for the Barlow or power mate. So the eyepiece you're stuck with, the telescope presumably, that has, those are 2 fixed factors, and then just bring in whatever magnification you need from there. Yeah. Okay, thanks a lot for your time.